Looks like it's that time. We can start class. Sign-in sheet. I want to get that going around. What are y'all working on? Called what? No. Okay. This thing still following me? Yeah, it's following. I guess it just didn't follow that far. All right. Well, today we're going to continue talking about Newton's universal law of gravitation. I want to re-emphasize something for you to make sure y'all don't confuse big G, which is Newton's universal gravitational constant, with little g, which is the mass, the acceleration of gravity on the surface of the Earth. In fact, according to the Newton's universal gravitational law, the force of gravity between any two objects is his constant times the product of the two masses divided by the square of the distance between them. Mass 1, mass 2, divided by r squared times his gravitational constant. On the surface of the Earth, we know that this is also equal to the mass of the object times the acceleration due to gravity, or little g. Knowing this, we can solve this equation for the value of g by simply dividing out the two masses. We find out that Newton's gravitational constant times the mass of the Earth divided by the radius of the Earth squared gives you the value of little g, or 9.8 meters per second squared. Which is real handy, except who knows the mass of the Earth? We don't even know that it's uniformly dense. I know that you hit a pocket of coal and it's going to weigh a lot less than if you hit a pocket of granite. I'm pretty sure that the cubic foot of the Sahara Desert does not weigh the same as a cubic foot of the ocean. So, you don't even have a uniform density upon which to go by to how do you even theoretically guesstimate the mass of the Earth? Well, in point of fact, till we had Newton's universal gravitational law, we didn't know the mass of the Earth. We didn't even have a good guess. Look in your books on page, page 120. Turns out that what we did was we measured the value of g, the universal gravitational constant. And that you can see the apparatus used here on figure 518 on page 120. Where, how many of you are familiar with the term optical lever? You know what an optical lever is? You know that, well, take a mirror, shine a laser on it. And if I hold this piece of paper here and I move that mirror back and forth just a little bit, I'm only going to move the dot, the laser dot on that piece of paper just a little bit. But if I take that piece of paper and I put it all the way up against that wall, now if I move that mirror just a tiny little bit, I'm going to move that dot over several feet. Well, that's called optical leverage. It's also why if you look through a telescope, you don't have to move that telescope but just a little bit before whatever you're looking at is completely out of your field of view. That's why telescopes have spotting scopes on them, so you can aim them and get an idea of what you're looking at before you try to figure it out looking through the telescope. This apparatus, it was actually kind of ingenious. Took a pair of balls, were known mass, mounted them on a stiff rod, and found the balance point, and suspended them from a string. So they were perfectly balanced and hung flat. And then attached a small mirror to that string. Now, took a long way away and put a scale on a wall and used whatever, but they didn't have lasers at the time, so they just used a very narrow beam of collimated light and shined it on that mirror so it reflected onto that gauge, gauge on the opposite wall, so that if this moved even a tiny little bit, they could see that reflected light move quite a distance on that gauge at the other end of the room. Then they took a ball on a rod, the same mass as this, and held it close to it and measured how far it moved that beam of light on that gauge. And doing so, they literally measured the acceleration due to gravity between the two balls. And that's how they came up with an empirical measurement of Newton's big G, his gravitational constant. Once that was measured empirically, that was the first time anyone was able to come up with even with any kind of quantitative value for the mass of the Earth. The radius of the Earth was known. I mean, measurements of the Earth's radius had been made all the way back to ancient Egypt, which is a whole other story. I don't know if any of you are familiar with that, but it had to do with a guy noticing that on a particular day of the year, the sun shined exactly straight down a deep well, so it perfectly illuminated the whole bottom of the hole. And he knew that on that day, he could go to some other distant location and dig a hole the same depth and find out at that time of day how far the shadow cast. Anyway, he came up with that's the technique he used to come up with an estimate for the radius of the Earth. Turned out to be a pretty accurate estimate, too. It wasn't exact, but it was pretty close. At any rate, like I said, the radius of the Earth had been known for, it had been measured many times and was known to fairly significant accuracy. The acceleration due to gravity was also known. That had been measured. We've measured it ourselves right here in this lab and found out that we measured it pretty close. Once they knew G, then they were finally able to plug all the numbers in and calculate the mass of the Earth. That's how the first calculation of the Earth's mass was made. Came out, and we're not going to go through and do it, but right here in section 5.6. It comes out to about 5.98 times 10 to the 24 kilograms is the mass of the whole planet. And this is where that was first determined. This is how it was first determined. We've talked about satellites and weightlessness, and what is true weightlessness and what's actually, when you're in orbit, what just appears to be weightlessness but isn't really. And we did do the calculation, didn't we, where we calculated the geosynchronous orbit and found that in order to have a geosynchronous satellite, it had to be at that specific radius from the Earth and had to be traveling at that specific velocity. Is everybody here for that? Was anybody here for that? Does this even sound familiar to some of you? Show of hands, come on. You were here. Who else was you were here, okay. All right. Well, we also talked about Kepler's laws. We didn't go into them, but we are today. They're actually kind of important. They're very important to astronomers, and they're not unimportant to the rest of us. In fact, I believe I pointed out to you that because this whole notion at the time that Newton was first introducing his law of universal gravitation, the whole notion of a force acting at a distance was just too foreign to people. They didn't really want to accept it. Even though they understood that, well, there's something makes the apple fall to the ground when it falls off of a tree branch. And they knew that that force at a distance could happen, that it did happen, because they were familiar with magnetism. And they knew that magnets would attract metal things from a short distance. What Newton was suggesting was a force that acted over these vast, great distances. And that was a bit much for people to accept. But what had been accepted were Kepler's laws of celestial motion. And it was because people had already accepted those laws of celestial motion that Newton was able to use them to demonstrate that his universal gravitational law subsumed all of Kepler's laws. Has anyone not signed this yet? What do I mean when I say that he showed that his universal gravitational law subsumed all of Kepler's laws? Well, Kepler's laws, Kepler developed his laws not based on any theoretical explanation. He simply made observations, very accurate, precise, measured observation of the motions of the planets in the sky relative to the sun based on the heliocentric model of the solar system. And he came up with these laws just based on strictly empirical measurements and analyzing the data. What Newton showed was that based with his purely theoretical law of universal gravitation, all of Kepler's laws could be derived theoretically and confirmed. Or basically he used Kepler's laws, Kepler's empirical data, to confirm his theory of universal gravitation. So we're going to look at that a little bit today. Now you remember, I told you that at the time, there was a belief that there were two separate realms. There was the celestial realm of motion and the terrestrial realm of motion. And the laws of motion in one realm had nothing to do with the other. They were two separate things. Kind of the way at the time they thought there was this thing called electricity and it did stuff, and there was this other thing called magnetism and it did stuff. But they were two totally separate things. They didn't have anything to do with each other until later Maxwell came along and showed that in fact they do. And well, that's what Newton did when he came up with this universal gravitation, was he united the celestial motion and the terrestrial motion. So let's take a little bit of a closer look at what they knew about celestial motion at the time. Kepler's first law. The path of each planet around the sun is an ellipse with the sun at one focus. Path of planets are ellipses with the sun at one focus. Does everybody understand ellipses, foci? Yes? No? Okay, you understand that a circle, a perfect circle, is just a special case of an ellipse where both foci are coincidental, both foci are at the same spot, the exact center. Well, at the time, the heliocentric model of the universe, or of the solar system, actually it was of the whole universe, but they actually believed that the stars were, also orbiting the sun, just at this great distance. The basic model of the heliocentric model started off with everything moving in circles, because that was the notion of celestial motion. Everything moved in perfect circles. This was revolutionary. I mean, to us today it sounds kind of, okay, so it's an ellipse, big deal. Well, this was important to them, because this was the first time anyone suggested that celestial motion was not necessarily in perfect circles. That it was, because up until then they accounted for all of the variations they saw, the retrograde motion of planets, things like that. They accounted for them by having everything move in smaller circles along paths of greater circles. And I've pointed out to you that mathematically that's fine, you can do that. But this was the first time anyone said, it's not really a circle, it's an ellipse. And there are two foci of the ellipse, and the sun is at one of them. And that's why everything is orbiting the sun, because everything is orbiting that, they're orbiting the two foci of their ellipse. Now, granted, he also pointed out that these were very nearly perfect circles, that the two foci were really very close together, but they weren't exactly coincidental. Let me ask y'all a question, and I really do. I want you to participate at this point. I want you to think about this and actually answer the question. Which model of our solar system is the actual true model of the solar system? The geocentric, where everything orbits the Earth, or the heliocentric, where everything orbits the sun? Say again? Heliocentric? Who else? That's kind of going to be the pat answer, right? Because, of course, everything orbits the sun. And everything does orbit the sun. But everything outside of the Earth's radius also orbits the Earth. Mars goes all the way around the Earth every 1.8 years. So does Jupiter, Saturn, Uranus, Neptune, and Pluto, which is still a planet. So if that ever comes up on one of my tests, Pluto is a planet. And it's also a cartoon dog. Getting back to the heliocentric model of the solar system, it really isn't exactly true. No planets do orbit the sun. They are kept in orbit by the gravity of the sun. But they don't orbit the sun exactly. They and the sun both mutually orbit a point in space that is the center of mass of the two bodies. Okay? So if you take the sun here and the planet here, and you put a point right at the center of the sun, and you call that one of the foci, that's not true. What is true is that there is if you take the sum of the masses and you find the center of mass of the both bodies, that is the point that both of the bodies actually orbit, including the sun. And now, in our case, that point is actually somewhere still inside the interior of the sun, I think. Not really an astronomer, so don't quote me on that, but the point is that it's that point that everything orbits. So while the planet is making this orbit, and I've drawn a very exaggerated ellipse here. It's actually much closer to a perfect circle than that. But at the same time, the sun is orbiting that same point. Like so. Let me give you see if I can give you a little bit of an intuitive understanding of what I'm talking about. Imagine you have a small ball and a big ball. And the small ball is attached to the big ball on a stick, a light, very negligible stick. And then you suspend that big ball on a string so you can hold it between your hand, hold it up between your hands. Now, if you start spinning that ball on the stick, so it spins around that big ball on the center of the string, that big ball is not going to stay perfectly in the middle of the circle. What you're going to find happening is that as the little ball moves around, the big ball also wobbles back and forth. Can everybody envision that happening in your mind? That is actually what happens when planets orbit stars. And it actually gets a whole lot more complicated than that because, as Newton pointed out, all of the planets actually attract each other as well. So everybody's orbit is completely affected by everybody else's orbit, including the wobble of the sun. But this is a pronounced enough effect that it is exactly how astronomers first began to discover planets in other solar systems. And that's only been within your lifetime that that's happened. Seriously. You were born. When you were born, scientists still did not know for a fact that there was another planet orbiting another star anywhere in the universe. They might have suspected, they might have believed, well, it has to be because that's the way that's just the natural way things develop. But it was only within your lifetimes that anyone was able to actually confirm the existence of an extrasolar planet anywhere. And that's exactly the technique they used to do it. They saw stars, they saw a star wobbling in its orbit around the center of the galaxy and realized that can only be happening if there's something orbiting it around with it. Of course, now they've identified and plotted and cataloged hundreds of extrasolar planets. But back to Newton and Kepler, none of that was known yet. So when Kepler first said that motion of planets is an ellipse, not a perfect circle, that was kind of earth-shattering. That was a seminal moment for science, for astronomy. What's his second law? Each planet moves so that an imaginary line drawn from the sun to the planet sweeps out an equal area in an equal period of time. Equal area in equal time. So that if this is the sun, here's the earth, it moves for this much time, whatever this delta t happens to be, it sweeps out this arc, delta L, through some angle delta theta, and the total area of this is some calculable number. Well, you then go out here to Jupiter, and you sweep out, you measure its motion in the same amount of time. It's not going to move near as far, but this area is going to be the area of that triangle, for lack of a better word, even though it's an arc on the end of it, not a straight line. This area and this area, as long as the amount of time is the same, both of those areas will be the same. That is Kepler's second law of motion, and that's his most famous one. That planets sweep out equal areas in equal time. Now, his third law, this one gets kind of long-winded. Let's take it. I'm just going to read it from the book. It says the ratio of the squares of the periods of any two planets revolving around the sun is equal to the ratio of the cubes of their mean distances from the sun. Okay, so here's law 3. Now, you know what? They use S in the book. I'm going to use S here too. S being the average distance of that planet from the sun. So, what's the period of Earth? Actually, when you throw in leap year, it's 365.25 days, and there's more decimal places there. It's not exactly every. There are also leap minutes and leap seconds, and they have to make corrections to that every. You'd be surprised how often they have to correct at the NIST, National Institute of Standards, something. It's an interesting tidbit for you. How many of you are familiar with the Jewish calendar? Any at all? Well, unlike the Earth calendar, or unlike the Earth, unlike the, what do we call ours, the Gregorian calendar? Unlike the American calendar that has the year divided into 365 and a quarter days, the Jewish calendar is based on the lunar month. So that the time between from one full moon to the next full moon is 1 month. Which is what? The sidereal or the synodic period? Yeah, don't worry about it. Doesn't matter. That's not gonna come back on any of your tests. So don't panic. Doesn't really matter. The point is that the Jewish calendar is based on the lunar month being 1/12 of the year. But they also, every time they get, every time it turns out that they get to the end of the 12th month and spring is still a month away, they just add a 13th month to their calendar, a kind of a leap month. And it happens actually more often than you would think. They add a month every few years. They also make other corrections to their calendar, but it's all very much observationally based. And that is the whole point. For the Jews, you're a nomadic shepherd in the Middle Eastern desert raising sheep. Whenever it's time for you to start observing one of those holy days or feasts that they had to observe all the time. How does a nomadic shepherd in the middle of the desert, Middle Eastern desert, how does he know what day it is, what day is? He doesn't. They keep track of what month it is. And when they see a new full moon, they know that, okay, it's the first of the month. And they start counting the days from the full moon to know what day they need to stop, when do they need to start whatever feast they're starting. They didn't have to worry about keeping track of calendars. Now, here's the question. And they do make lots of corrections to their calendar. They add a whole month every so often, and they add extra days here and there because who do you think corrects their calendar more frequently, them or us? Americans and Westerners in general get pretty anal retentive about being precise, about knowing exactly what the right number should be. And all of those extra little decimal places means the Western world ends up correcting their calendar quite a bit more than even the Jews correct their observational calendar. And they don't even try to keep track of how many days there are in a year. It's like some years they have 360 days, other years they have 364 days, other years they have 350 days. But they actually end up correcting their calendar less than we do because we actually try to keep up of all of those leap minutes and leap seconds where, we didn't quite make it all the way back to the starting point at the end of this year, and those add up, and so every so often, a few milliseconds here, a few milliseconds there, before you know it, you're a whole second off. So, anyway, that was just a side note. I think it is germane for anyone studying physics or any of the sciences, because it speaks to the notion of precision and accuracy, and basically it begs the question, if you can't tell the difference, does it matter? So, anyway, period of Earth, 365 and a quarter days, give or take. Actually give, because it's a little more than that. Who knows S for the Earth? The mean distance from the Sun. Anybody? Got even a guess? Read that again. Times 10 to the 6 kilometers. Okay, that sounds about right. In English units, it's 93, roughly 93 million miles. But there's an even simpler answer. Exactly. Give the man a Cupid doll. 1 AU, 1 astronomical unit. Just now, what is the mean distance of any planet from the sun? The average distance it will be from the sun. And this is why the book uses the letter S for distance. Remember, the orbit is not a perfect circle. It doesn't have a radius. It's an ellipse. It has a major axis and a semi-major axis. And the mean distance from the sun is the semi-major axis of the ellipse, or based on the semi-major axis. Okay? That's why they call it S instead of R or D. S stands for semi-major, or semi-major axis. So, they give you a better description here in the book under Kepler's laws, under Kepler's third law, but we're not going to go into the geometry of it. Now, what does this mean? It means that for any planet, the ratio of its period to its we're going to do this. Just do this the way they do it in the book. We can rewrite this. Come over here. We've got T1 squared divided by T2 squared is equal to S1 cubed divided by S2 cubed. So, we divide both sides by S1. And multiply both sides by T2 squared. We find that the ratio of the square of a planet's period to the cube of its mean distance from the sun is a constant for every planet in the system. It should be the same value. I think there's a table in the book here, if I remember. Where is it? Oh, right here under my nose. Table 5.2 at the bottom of page 126. And it lists the actual measured values of S cubed to T squared, which is the other way around, but still, for all of the planets. Now, I do want to do this. Hopefully we can do this quickly before the class is over. I want to go through and look at how we would use Newton's universal law of gravitation to derive Kepler's third law. Because this is how Newton got convinced people to accept his universal gravitation. He showed that Kepler's empirical data confirmed his theory, which made it law. Because in all of science, until it's empirically confirmed, it ain't science. All right. The sum of the forces. Let me just start over here. We've got the sum of the forces is equal to mass times acceleration. Now, that means we've got Newton's universal gravitational law giving us mass of the Earth times mass of the Sun divided by the distance between them squared. That is going to be equal to mass times acceleration. Well, the Earth is moving in basically a circle. So, okay, not exactly a circle, it's an ellipse. We're not going to go into that much depth. Mass of the Earth times v squared over r. It's centripetal acceleration. Now, I'm using Earth, but we could just make this any of the planets. This could be just M1, or it could be mass of Venus, mass of Saturn, Mars, Jupiter, any of them. All right, so we need to know its velocity. Well, what is the velocity? Distance by time. So how far does it travel? It travels 2 pi r, the circumference of its circle, of its orbit. And it does so in what? In one period, 1 year. So we're going to call this radius of the Earth and the period of the Earth. Well, we can plug that in here. And we've got mass of the Earth times 4 pi squared, radius of the Earth squared, divided by the period of the Earth squared. Say again? Did I miss something? Oh, I sure did. I've got v squared, but I still need to put it over the radius of the Earth, which will cancel one of these. So we've got, thank you, good catch, mass of the Earth times 4 pi squared radius of the Earth divided by the period of the Earth squared. Now we can rearrange that if we multiply both sides by t of the Earth squared, and divide both sides by the radius of the Earth, we end up with the radius of the Earth cubed cancel out both of the masses of the Earth. That leaves 4 pi squared. And we have to divide by g times the mass of the sun. Well, what is r cubed? That's r is the same as the s over there, so what we wound up with here is the period squared divided by the radius of the Earth is equal to 4 pi squared times divided by gravity by the mass of the sun. But notice that this side has nothing to do with the Earth. Right? So we could do this same exact derivation for any other planet. And we would get the same result for that planet. They're both equal to this constant that doesn't change. So we end up with this. Period of 1 squared divided by the semi-major axis, or the average distance of radius of that one squared, cubed, is equal to the period of the other one squared divided by the radius of that one's cubed, which we got by rearranging from Kepler's third law. And so Newton's universal gravitational law just subsumed Kepler's third law. And I would point out to you that, as they do in the book here in example 514, I've got several minutes left. What here do we not know? We know the period of the Earth, right? We know the average distance of the Earth from the sun. We know g, the universal gravitational constant, because that was measured. That means with this, we can now calculate the mass of the sun. Mass of the sun would be equal to 4 pi squared divided by g times the average radius of the Earth cubed divided by the period of the Earth squared. And those are all numbers we can plug in. Let's see, here we've got the radius of the Earth. (1.5 times 10 to the 11 meters cubed. That doesn't sound right. Radius of the Earth. Are they using the Earth? (1.5 times 10 to the 11). Okay. According to, oh, this is kilometers, and then you go to meters. Yes, okay, never mind. Yeah, 1.5 times 10 to the 11 meters cubed, not kilometers. There's g is 6.67 times 10 to the minus 11. And the period in seconds squared. And it comes up with about 2 times 10 to the power of 30 kilograms as the mass of the sun. Point is, once people began to understand these things and started coming up with numbers that they could empirically measure, and they could then start calculating and finding out what is the mass of the sun. I mean, how before this, how would you even have begun to guess at the mass of the sun? Okay? Have you ever looked at some of these stories that come out of NASA where they talk about, well, they know that the mass of this planet is this much, and wondered how? How do they know how much a star in a galaxy 600 billion light years away, or however far it is, how do they know how much that star weighs? What's its mass? This is how. But more than that, I pointed out to you that they use that knowledge that the sun wobbles, that the planet doesn't exactly orbit the sun, that the sun and the planet both orbit a point in space that's the center of mass. Well, they use that to determine where other planets exist in other solar systems. And also then we're able to measure the mass of that planet and the mass of the sun that it was, the star that it was orbiting, just by making observations like this. But even more closer to home, when Newton and Kepler were doing all of this, basically the only planets we knew about were Mercury, Venus, Earth, Mars, Jupiter, and Saturn. I don't know that they even knew about Neptune at that point. But they did, once they began to understand that, wait, there are discrepancies in these laws of motion that Kepler predicted, and they can be explained with Newton's universal gravitation, that there are perturbations when all the other planets are acting on each other and changing up the way they orbit. So they started using those corrections and realized that, whoa, wait a minute. These perturbations are being perfectly explained, until they got to Saturn and said, wait, what happened? Why did Saturn do that? Why did Jupiter do that? Those can't be explained by the rest of the planets. And they concluded, oh, well, there must be other planets out beyond Saturn that we don't know about. And that's how they discovered it. They discovered Saturn, Uranus, because of the effect it had on Saturn. They discovered, and they calculated and said, well, if it really does exist, then this is where it should be. And they pointed their telescope in that direction, and sure enough, there was this big old planet, big old honking planet sitting out there at the edge of the solar system that they'd never noticed before. And by doing the same thing, they discovered Neptune and even Pluto later, which is why, even though there are other dwarf planets beyond Pluto, that they don't want to call them planets, they want to call them dwarf planets. What do I care? But in point of fact, Pluto was significant enough that the perturbations that Pluto caused to Neptune, that's the second to the last one, yeah, Neptune. The perturbations that Pluto had, the effect of Pluto on Neptune, were significant enough that they were able to calculate them and say, if there is a planet out there, here is where it should be. They looked and boom, there's Pluto. That to me earns it a place in the catalog. And it's 5 till the half hour, so class is over. I will see y'all on Friday, and we will finish up this chapter. We do have a lab tomorrow. What we're actually going to do is sit at these computers and look at simulations of gravity and orbital effects and things. Thank you.